Hi, is anybody on? Oh yeah, we have a couple people on Zoom. No, maybe one person. But on Zoom too, I can try to look and see if you want to ask a question in the chat will pop up. So we'll see how well we can manage that. But especially for the students, like just starting your career, these are some things that I kind of wish that I had heard earlier in my career. And for my fellow faculty, mid-career, dare I say, faculty, like how did I get here? But maybe keep this in mind when you're mentoring students in terms of potential career paths that they can take that are, you know, increasingly not like the traditional faculty career path, but then again, what is the traditional faculty career path? Let's explore that a little bit. So just to give you a little bit of so I'm at the Macaulay Honors College of the City University of New York. So CUNY is the City University of New York. It's our urban public institution. There's, you know, 1 billion campuses across the city. But the Macaulay Honors College was founded about 20 years ago. It's weird in that it does have a campus. There's its campus. It's a brownstone on West 67th Street, very close to the Museum of Natural History, which is nice. But there are 8 programs for the Macaulay Honors Program on 8 of the senior CUNY colleges spread across the 5 boroughs. But the reason that I'm in CUNY and in New York City is really CUNY Astronomy and Astrophysics, which is something kind of differently entirely that we've made ourselves. And I think some of you might be familiar with it, but it seems like as our community grows, we've kind of gotten fractured again. And you know, there's too many of us to fit in this small room again, so we don't see each other as much as we used to. So CUNY Astronomy and Astrophysics now is our kind of accumulation of astronomers across the different colleges at CUNY. And so this, our little constellation, of course, that we made is every single campus. We don't have an astronomer at all of the colleges or at all of the campuses. I kind of use those words interchangeably, but they imply different things. I won't go into that. But we have 10, so we have 16 astronomers now spread across 10 of the colleges at CUNY, including, those are mostly undergraduate colleges, but we also have a graduate center across from the Empire State Building where we have a PhD program in physics, where we can mentor students in astrophysics projects. But we also now, as of the last couple of years, have a master's program in astrophysics at the Graduate Center, also funded by the Simons Foundation, which is where all of our best lunches come from, right? And CUNY kind of continuously, but sporadically is still hiring people. And so we've got a couple new hires recently. The most recent one at Queens College and City Tech, I believe, were the 2 that started the most recently. And so always, you know, check our cunyastro.org faculty page to find the new people and invite them as well. We all have something different to say. And just to remind you, so that the CUNY faculty, you probably already know a bunch of us either from AIM&H or from the Center for Computational Astrophysics, where a lot of people have research associate appointments at one or both places. And I just want to plug our amazing kind of the program that brought us together is this AstroCom NYC program. That's this, instead of a bridge program, I think of it as an on-ramp program for undergraduate students. And so it's for CUNY students, especially from students from underrepresented backgrounds, because that's really the majority of the students at CUNY, which is wonderful. And then retaining and supporting them through generally a physics major or some other science major, preparing them for graduate study in astrophysics through their undergraduate careers. And so that's funded by the National Science Foundation as well as by the Simons Foundation. And they get to work at AIM&H, they get to work in CCA, and so they're very much a part of our New York City Astro community, which is wonderful. Okay, this is my research focus. So my research focus is brown dwarfs, and I'm going to give you kind of a very broad overview of what brown dwarfs are, why we think they're important, and kind of what are the outstanding questions about brown dwarfs, at least from my perspective. I think Jackie Faraday was here not too long ago, and so it'll be interesting to see, okay, there'll be a quiz, no. How much you remember, but also how much I say that's similar, how much that's different, because I think part of the interesting thing about brown dwarfs is that we're really still, for these objects, we're in kind of the initial discovery phase for these astrophysical objects, which like doesn't happen too much anymore. You know, some of the, I'm getting ahead of myself, but some of the things that we're doing with brown dwarfs are very similar to what we were doing with stars 100 years ago. It's a lot messier, and you know, the computers are machines and not people, and they're paid a little bit better. But so these brown dwarfs, just to remind you of what they are these things that we kind of the simplest way that we explain them is that they're in between stars and planets, or intermediate between stars and planets in their physical properties, which, like everything in Astro, is, you know, simple enough to be just wrong, just straight up wrong. And so even though we put these in a nice line, I'm going to spend the rest of the part about brown dwarfs explaining how this is wrong for the most part. So the sun here, this is nicely, I think it's a beautiful artistic representation. It's kind of our go-to one for brown dwarfs. The sun is over here, an M dwarf star is here. These two ones are kind of the brown dwarfy objects, and then of course Jupiter over here on the right. Or maybe I shouldn't take it for granted. Jupiter, the biggest planet in our solar system, that's for the physicists. Over there on the right. And you can see the important thing, or one of the important things to notice here, is that everything is spherical. You know, we see a full disk except for Jupiter. We only see Jupiter and its reflected sunlight. And so that's, you know, one way that you can tell that it's a planet and not a free-floating object that's radiating kind of its own accord.
And the sizes in that are to scale.
Yes, we do believe the sizes are to scale. This is kind of an open question, like what the actual radii of the objects are, but for the most part, yeah, they seem to settle down, even though, so I should also, yeah, so the, there's temperature differences as we go across, there's mass differences as we go across, kind of whether or not those are clearly delineated is my, like, that's kind of wrong. Like kind of saying that brown dwarfs are separate from stars or planets in kind of any of these physical properties now is maybe becoming disfavored, except for one. So I will say the one in between the star and the brown dwarf, that's a nice clear delineation. And that's a hydrogen burning minimum mass. And so these brown dwarfs are really the clearest way we can find them right now is that they're objects that are not enough, I could turn it around and say it in a positive way, they're too low mass to fuse hydrogen into helium stably. Right, they just don't reach a high enough core temperature to ignite the hydrogen fusion and have it continue in order to counteract the gravitational forces of the material. And so above a certain mass, the star will become a star, the engine turns on, and it actually slowly fuses its nuclear fuel for billions, if not trillions of years, based on our understanding of the emitted radiation. But for a brown dwarf, that's just not going to happen. At least stably for a long time. I'll talk a little bit more about what will happen, but that's a pretty clear difference and ends up having a big impact on the overall evolution of the object. On the other side of the brown dwarf, though, between the planet, between the brown dwarfs and Jupiter, that's a bit more of an open question. And we used to go to theory for this, and we used to say that, okay, there's a hydrogen burning minimum mass, it's around 75 or 80 times the mass of Jupiter. And then there's also a deuterium fusion minimum mass that is about 13 times the type of the mass of Jupiter. And so we used to say, okay, we're going to call the things that are in between those two masses brown dwarfs. But really that isn't super helpful and doesn't actually make a lot of sense given the other properties of these objects. And so I'll come to that. But I want to also remind you, especially if you're teaching Astro 101 or something like that, that we have new spectral types for these objects, relatively new. So after the OBA FGKM, we have new spectral classes L, T, and Y that nominally correspond to cooler and cooler temperatures beyond the M dwarf stars sequence. Not all L dwarfs are stars. Not all L dwarfs are brown dwarfs, not all M dwarfs are stars, but I'll get to that a little bit. The T dwarfs are, for the most part, brown dwarfs, in terms of their mass at least, but exactly what those masses are is a little bit unclear. Some of our T dwarfs are coming out a little bit too heavy when we are able to measure their masses, which is fairly rare, and so maybe it's not a huge problem yet. And then the Y dwarfs are the newest one, so only really fully confirmed in 2011 with results from the Wide Field Infrared Surveys Explorer, the WISE mission, but only a handful of them are known, and we really only have the spectral types defined through like kind of Y0, Y1, and then they become Y question marks, and we don't really know. I think JDUST will be able to go after these a little bit more, but I'm not sure if anybody's actually doing that yet. So in theory, these correspond to temperature in terms of the spectral classes, just like the stars, but they don't. And I'll show you why in pretty much right now. So I don't have the Y dwarfs on here because the spectra, the SEDs are even more incomplete, but these are SEDs, spectral energy distributions, pre-JWST. These are as good as we could get for a handful of kind of prototypical objects. So this is a project that my grad student did, nearly a decade ago, which is kind of frightening. But it looks like a nice kind of sequence from the late M through a mid T dwarf. You know, it a little bit has the shape of a black body still, but you can see that there's just a lot of absorption coming out of that, kind of eating away at the black body from the atmospheres of these objects. So you have a lot of molecules forming in the atmosphere. You have even very broad alkali lines and things like that. There's a lot going on that just you lose the shape of the black body underneath, and it becomes really like emission windows through the outer layers of these objects. But in generally, at least overall, the total flux emitted by the objects decreases, like you might expect for objects around the same radius that are decreasing in effective temperature. Like, you know, it gets messy, but we also think we understand, like, you know, when certain molecules become strong absorbers and things like that, like maybe we're okay. But there's a lot more complexity that comes into these objects because of the difference between the stars and the brown dwarfs. And that's that the stars, when that stable hydrogen fusion kicks on, the objects don't change for most of their main sequence lifetime. And so these are evolutionary models kind of showing tracks for objects of different masses with age on the x-axis, luminosity on the y-axis, but really luminosity could also be temperature, it could also be radius, because a brown dwarf, unlike a star, is not going to have that stable source of energy at its core, and so the brown dwarf is going to cool, fade, and shrink with time. And so the stars up here are really the stellar masses, so the more than the hydrogen burning minimum mass. And you can see that it takes them a long time to flatten out, but they all do eventually flatten out. And that's the hydrogen burning becoming stable. But below that, these are the brown dwarf mass things. They never really flatten out. There's some kinks up here where I kind of think about it as an engine that might turn over but never quite catch, which I'm going to have, like when we all have electric vehicles, I'm going to need a new analogy because that doesn't happen with electric vehicles, I don't think. And so they might fuse a little bit of lithium, they might fuse a little bit of deuterium, but there's not enough of those elements, and they don't have the energy output to become a stable source of energy against the gravitational collapse. And so these objects don't ever kind of stabilize like that. The brown dwarfs just continuously cool and fade with time. And so that's the steady decrease through the green ones. Now, the thing that I don't like about this plot, but I haven't fixed yet, is the difference in between brown dwarfs and planets. So the brown dwarfs are colored in blue, in green, and the planets' tracks are colored in red, really at this arbitrary 13 Jupiter masses. But you can kind of see that, you know, there's some weirdness going on at just above the 13 Jupiter masses, but below the 13 Jupiter masses, they're much smoother all the way down because there's no fusion, there's no like engine turnover at all. And they just do the same steady decline that the brown dwarfs do. They cool and fade and shrink a little bit with time.
Does any, first, like Jupiter, I have this memory from the deep dark past. Jupiter has like radioactive decay contributes some aspect of its luminosity, some amount of luminosity.
Jupiter is too warm for how, there's some aspect, like Jupiter is too warm for where it is in the solar system to be just reflected light. And so there is something else, you know, it could be a little bit of leftover heat, but after 5 gigayears, you know, that's kind of a long time.
But in these models, is that thought to matter at all?
I don't think we put that in at all, no.
Okay.
It's going to be very, very marginal, if anything. Okay. Yeah. Oh my God. Right. Don't ask about. We can talk about dust, but don't talk about magnetic fields with these. Anything. Yeah. Radioactive decay, like, you know, it is going to be very, very marginal.
Very marginal.
For any of these things. Yeah. So what this ends up causing is an age mass degeneracy, and that's what the squares are meant to represent. And so when you observe one of these objects, you generally, like observational properties here, I picked luminosity to show, but sometimes we pick temperature that nominally comes from our spectral type. And so sometimes on the right side over there, I put a spectral type sequence. When you pick that, you don't actually know what mass of an object you're observing unless you also know the age somehow independently. And so that's when we were starting to find young brown dwarfs and trying to kind of calibrate these sequences and compare to models. We were looking for things in binary systems, or we were looking for things in young clusters to be able to have an independent constraint on age. And then kind of from these evolutionary models, back out a mass. We can get dynamical masses for some things, but only when you have a binary. You can resolve them. You could do independent astrometry or radial velocity measurements. That's really Jackie Faraday's area of expertise, and so I'm not going to talk about that too much. I focus on the spectra for the most part, but it's still a pain in the butt, because if we define these things by masses, we're really just kind of guessing, unless we really trust the evolutionary models, which, you know, the observers know better. Well, I think the observers trust them more than the theorists do sometimes. And then when we go back and try to figure things out just using our observational data, knowing that something is young, for example, throws an even bigger monkey wrench into the system. And so here's the same kind of SED plot, and the objects that I had showed you before, color-coded, are now gray in the background. Those are meant to be our kind of scale of the kind of old field objects, the things that have, at the most part, you know, they're not settled into a main sequence, but they've reached to a pretty stable radius, a pretty stable gravity, and they're going to change even more slowly with time. And so to that extent, they end up being a little bit similar to stars. But then we throw up some young objects on here, and the young objects are kind of all over the place and crisscrossing the various spectral types, you know, much more luminous at some wavelengths, underluminous at other wavelengths. It's this one other parameter. So youth is also corresponding to an inflated surface gravity or an inflated radius for these objects, because they're still cooling and shrinking with time. And so a younger object is going to have a lower surface gravity, kind of a lower pressure. They can have more extended atmospheres. And so this kind of secondary parameter that for stars, this luminosity class is very easy, well, not easy, but, you know, we kind of take it for granted that we can measure a luminosity class separate from a spectral type for a star. For brown dwarfs, we can't yet do that. We try to by giving things these kind of gravity designations, but they're different in the optical versus in the infrared. They're not always consistent with age that's independently constrained from binary systems or from clusters. And so this is as yet an unsolved problem of just this secondary parameter in the spectral understanding of these objects. And then you get into the tertiary parameters, which is where things really start to get interesting. And so interestingly enough, their very first confirmed brown dwarfs and their very first confirmed exoplanets were discovered around the same time. They were actually announced at the same, I want to say it was a Cool Stars conference in Italy in like 1995. You know, everybody remembers though when 51 Peg was announced, and nobody remembers that that was when Gliese 229b was announced, because the exoplanets like exploded from there. And we actually know there's more confirmed exoplanets than there are brown dwarfs. And so very quickly, brown dwarf people were like, oh, these are exoplanets too. Like, so we promise. Yeah. And so that's the way that we got funding, by saying like, oh, these are, you know, kind of laboratories for understanding exoplanets, because the brown dwarfs are out there on their own for the most part. So we can get, you know, higher resolution spectra. We don't have to worry about removing starlight. We don't have to worry about you know, secondary eclipse measurements and things like that. We can get like straight up direct emitted spectra from these objects. And in theory, the atmospheres should kind of be similar or continuous from a very cool low mass star where you have molecular gas, and maybe you have some high up condensates forming. And then as the object becomes cooler and cooler, you get even more complex gases. And so, yeah, there should be methane up there. There should be ammonia clouds high up there, and kind of more complex clouds forming. And the atmospheres for these objects really shouldn't care whether they're a brown dwarf or an exoplanet for the most part. It really should depend on just the, the fundamental properties, like the temperature, the surface gravity, to a certain extent, the composition that's there. And so I'll talk about that in a little bit. But this was our, every NSF grant started with this, to say that, hey, these brown dwarfs, you're going to have similar atmospheric chemistry, similar atmospheric physics to these directly imaged exoplanets, but you don't have to remove the starlight for a brown dwarf. And so this is really the iconic directly imaged multi-exoplanet system of HR 8799, where there's, we can see these exoplanets. I still cannot get over this image. This is still one of my favorite astronomical images, even with all the JWST stuff that's out now. But there's an A star at the center that had to be removed in order to see these 4 planets. And now they're, Jason Wang, who I believe is at Northwestern now, has animated these data taken over the last decade, almost decade and a half, to show the orbital motions of all of these planets around a star, which I think is just amazing. But these planets are something like 5 to 10 times the mass of Jupiter. So we can get spectra of these planets using some even ground-based instruments like OSIRIS on the Keck telescope, but we're always going to be very limited in terms of the wavelength coverage, in terms of the spectral resolution, and even just in terms of the signal to noise, because we've had to remove, a 1.5 solar mass star in order to get the light from these planets. But these things are pretty obviously planets, but they overlap in mass with potentially free-floating objects. So we've also found, for the free-floating objects, we can't always dynamically determine the mass, but we do think we found free-floating brown dwarfs that are 5 to 10 times the mass of Jupiter. And so, I kind of hinted at the fact that this deuterium burning minimum mass really doesn't matter for anything. It doesn't really change the overall evolution of the object very much. And really, it seems like it doesn't matter for the formation either. We can have, more massive objects forming around a star. We can also have less massive objects forming on its own. And so here's what I think both best and worst definition of a brown dwarf is, because it's the best, in fact, that I think it's the most kind of meaningful definition of a brown dwarf is that a brown dwarf forms like a star does, from its own cloud of collapsing glass and dust. And a planet forms in the disk around a star. Like, pretty straightforward, right? But figuring out which is which is not as simple as like, oh, if it's around a star, then it's a planet, and if it's out on its own, it's a brown dwarf. And there's 2 reasons for that. One of them is that the solar system and the planetary formation people have convinced me that, massive things get kicked out of planetary systems, like possibly pretty frequently. Maybe we lost something in our own solar system, maybe it's long gone, or maybe it's just out past the Kuiper belt and my brown is going to find it. But also that I lost my train of thought just for a second. Yeah, and so like the formation, I think, is the most meaningful thing to get at for these objects, to differentiating between the two, because the mass, really doesn't matter. We can have, the other aspect of it is that we can have big planets forming around big stars. We have 5 to 10 Jupiter mass planets are on HR 8799. David Latham, I always feel very bad for David Latham at Harvard, because he, one of the first radio velocity planets, at the time they were like, oh no, it's too big, like it's not a planet because it's not below this 13 Jupiter minimum mass. But it turns out that it was, the radio velocity measurement has the M sin I factor in it always, and so I never remember which way it goes. But David Latham is the guy that everybody should know, right? And not only, the Swiss astronomers that got the Nobel Prize, because that ended up being a real companion, I think, on the massive end of things. It wasn't a half a Jupiter mass thing in a 4-day orbit, but nature does seem to make these big things around big stars as well. Gosh, I hate this. So as much as I love the brown dwarf planet connection, there's certain brown dwarf astronomers who took their very low mass free floating objects and called them rogue planets. And I think they did, I would like to give them credit and say that they did this because they talked to our our formation theory people and said, okay, these things get kicked out of the solar system so much, but I don't think they did. I think they called it these because they wanted the press release. And so on one hand, we have beautiful press release images for these brown dwarfs. On the other hand, I detest the phrase rogue planet. And if you want to sell me a rogue planet, I want to know that it came from a planetary system. Unfortunately, so as much as I think that that's the important aspect of these brown dwarfs, I also don't know how to be convinced that it came from a formation in a disk. The thing that I would put my money on right now is a difference in metallicity between, you know, the average solar metallicity or slightly super solar metallicity if you have younger objects nearby versus an even more enhanced metallicity for something forming in a disk. And so this is just one of the HL Tau from ALMA showing the beautiful protoplanetary disk with the rings and the gaps and things like that. In our own solar system, Jupiter and Saturn have much more heavier elements and volatiles than the sun does. And so the significant enhancement in heavy elements is a signature of being formed in a disk, and maybe even where in the disk you formed, although I think that's still very, very hazy. And so it would be great to, you know, find a rogue planet, measure its metallicity and say, okay, it's not just, you know, 0.2 of solar metallicity, it's 20 times solar metallicity. Then I would buy that as a rogue planet, having, even if you can't find me the system that it came from, I would believe that it did come from a system and form in a disk. But it's very, so we can't even get at youth or age or surface gravity, the secondary parameter from spectra of a brown dwarf yet. We definitely can't get really reliable metallicity measurements for a brown dwarf. And even then, metallicity is like oversimplifying it, because we can really do, what's more important to do is like more independent abundance measurements. And so we can start to get at it with retrieval analysis, which hopefully Jackie talked about a little bit. I won't go into it, you know, but even things like disequilibrium chemistry and C/O ratios being different is important to understand these cool objects, even without getting into very, very different metallicities. And so basically, the picture is complicated and it's job security as far as I'm concerned. Yeah.
How do you disambiguate between like molecules and the metallicity?
Yeah, so everything's going to go into, so the metallicity is going to take everything into account, and a lot of it has to do with, you know, kind of predicting what's going to condense out, what's still going to be in the gaseous phase and what's going to condense out, and kind of having those equations of state and condensation curves accurate, and having that all fit with what you observe for the objects. Yeah, and so we can do it, like, in, you know, a retrieval analysis can give you all of those numbers, but how kind of reliable those numbers are from object to object, you know, I wouldn't believe any individual one really quite yet. There's another question about that.
What is the reasoning behind a planet forming within this so much higher metallicity?
Yeah, that's a really good question. The reasoning behind this, and I'm probably going to mangle it a little bit, is that it's the heavier elements that stay in the disk and the lighter elements get blown away. Especially when it's kind of opposite for going further out. So further out you have more material because you're past the snow line and it's cooler and you retain some of the lighter elements as well. But in general, you're going to have, like, you know, also from the formation perspective of the core accretion model, where you start with a core that's going to be made of the heavy elements, and it's the lighter elements that are not going to contribute to that as much.
So even, or not to use the term you hate, but rogue planets or potential brown dwarfs, they would still retain the high metallicity even if they're getting kicked out.
Yes. Yeah, I think so. Like, if they, you know, if they formed in the disk, then they should form with that high metallicity. Right, in the core, where you know the initial collapse at the core, like, of the entire system, like, that's going to have our stellar metallicity that's, you know, slightly enriched in heavy elements as the more of a, you know, kind of on a galactic age time scale. But within the disk, the objects have higher metallicity. As you know, it's like, this is, you know, almost, the opposite of what we thought was obvious before, right? 100 years ago when we were trying to figure out the composition of the sun and the rest of the universe, it was like, okay, well, it's got to be like the Earth. And so there's got to be a lot of magnesium, there's got to be a lot of silicon, there's got to be a lot of oxygen. And then Celia Depayne-Gaposchkin did her spectral analysis and was like, oh, no, it's, 75% hydrogen. And all the Princeton dudes were like, oh, no, that's wrong. And she was like, oh, I'll put this in my thesis, it's probably wrong. Like if the students, especially if you don't know the Cecilia Payne-Gaposchkin story, it's an amazing story, like horrifying. Don't let your thesis advisors convince you that you're wrong. She ended up being right later on, and then I went off on a tangent, but did that answer your question? Yeah. Okay. There's another potential. I want to give this one one slide because people have been doing a lot of work on it. That another potential indicator is rotation, so basically angular momentum in a binary system. And the idea behind this one is that something that formed via co-accretion in a disk is going to have a more similar angular velocity kind of vectors within the system. And if they formed via separate gravitational instabilities, they're going to have more misaligned angular momentum vectors. And so this is, as you might imagine, very, very difficult to actually measure. You need V-sin-Is, so you need good spectra, you need rotation periods, photometrics, so independent for the two objects, so you need to be able to spatially resolve them as well. But it has been done for one companion-like system. It's a young system, and they're both, so the star is a low mass star of about 0.4 solar masses, and so maybe a mid to early M dwarf. And then the companion is this 12 to 27 Jupiter masses. And they think that these, the vectors that they get are different enough that they claim that this is evidence, not, the strongest evidence, but at least circumstantial evidence that these objects form kind of separately from gravitational instability, and so that this object should be called a brown dwarf and not a planet. Even if it's not super duper convincing observations, I like that they're using that, the formation argument as a way to name the object. So even though you might look at it and say, oh, it's a companion, the mass ratio isn't actually super high, and so it's not really a planetary companion necessarily. Which leads me to this one, which is the one, one of the first ones, and also one of the more controversial ones. The system is called 2MASS 1207, and it was discovered with the VLT, and so the press releases are kind of ESO-based, and the press releases call this the first directly imaged exoplanet, and nobody else does. And the reason why is because the primary is a 25 Jupiter mass brown dwarf, and a young brown dwarf. And the secondary, this is still a great observation to resolve these two systems. They're really canonical systems for the brown dwarf community, but it's like calling, I don't know, the moon and an Earth a planetary system or something like that. We're a double planet system really, but the mass ratio is 5 between these two. Unlike our solar system, which is 100 between the 100 or 1,000. Much, much bigger between the sun and Jupiter. And so, I would call this binary brown dwarfs. Some people still, because this is below that 13 Jupiter masses, kind of historically in the early 2000s, it was called the first directly imaged exoplanet. We still want to study these. We think that brown dwarfs are really numerous. We're not entirely sure about the mass functions for either the freely floating brown dwarfs or for the more massive companions, but the brown dwarfs are out there and there's a lot of them. And so they are really important to study, and hopefully I've convinced you that brown dwarfs are important to study. Maybe everything you knew about them up until now is wrong, but like I said, I call that job security. And I want to shout out to my research group. So BDNYC is my research group. So it stands for Brown Dwarfs in New York City. We had a little joke going because there's no Y train. Don't look for that Y train. But there's also, when we started the research group, there's no Y dwarfs either. And so then Mike Cushing discovered the Y dwarfs, and my joke went to heck. But so Jackie is full-time at the American Museum of Natural History. Kelly is faculty at Hunter College. Where is my time?
There's a clock right there.
There it is. Okay. I talked a lot more about my research area than I thought I was going to, honestly. So, because here actually with my research group is where I want to stop and shift, because for the last couple years, I've actually stepped away from the BDNYC research. I kind of want to blame the pandemic and having 2 little kids at home. It's one of these things, I don't know if you've heard this analogy of, you know, when you get further and further in your career, you have a lot of things to juggle. You have a lot of balls to juggle. And one of the things that you have to figure out how to do is tell the difference between the rubber balls, the ones that are bounce, you know, they're going to bounce and they're going to run away from you, and the glass balls that are going to drop and just break. And so the idea is that, like, okay, you know, the rubber balls are going to be fine. You can go find them in a corner, pick them back up again. The glass ball is going to break and be gone. At the beginning of the pandemic, I realized that, like, that Jackie and Kelly could take my glass balls. Like, they didn't have little kids at home. You know, everybody had their own things, but I had a 3-year-old and a 1-year-old at the beginning of the pandemic. And so the first thing I did was, like, make sure that all my research students were taken care of. And like, I haven't gone back and I don't know fully why, but I also want to tell the students in the audience that maybe that's okay. It's okay for me because I have tenure, but it's also okay to realize that you have other interests and to, like, share those other interests with the scientific community, and even to think about those things as science. And so here's I'm gonna go through this really quick. It's just words. That's too much. So I have tenure at CUNY. I'm pretty happy with where I ended up, considering that my parents didn't finish college. I never really said I wanted to be a scientist or I wanted to be a professor or anything like that. But somehow it seems like the further I go, the less I feel like I belong here. I don't know if it's because I didn't know better as a graduate student or what it is. This is for me and my therapist to figure out. But I 100% have imposter syndrome. I frequently considered, and still do consider, leaving academia. I keep applying for other jobs. Sometimes it helps me get a better job, which is great, or sometimes it helps me realize that I don't actually want that other job that I applied for. And even still, as a professor, I feel like I have to prove myself, and I feel like I have to, you know, live up to some standard that I didn't even know existed when I started down this path. And there's a lot of things that I do that I kind of either not hid, but, like, kind of tried to distance my professional self from, because I felt like they would make people not take me seriously. And now I don't care anymore. No, I don't know what, like, anyway, I'm gonna run through a bunch of them. Like, I started out being, like, knowing that I wanted to do astronomy because of being a planetarium presenter. Even before I went to graduate school, I picked UCLA for graduate school basically because they had a student-run planetarium. I came to AMNH for a postdoc because they had a planetarium. But this was very much like, you know, it was kind of a dismissive thing, like, oh, you're going to go to work in the planetarium, or you're going to work in the gift shop or something like that at the museum. Like, you know, no, it's a research center. I wrote a lab manual for astronomy. I did that, like, started at UCLA. It wasn't ancillary, but it was kind of like too much focus on teaching, maybe, at least for a little bit. I do these goofy videos at conferences. Some of them were started at the Astronomy conference, which is actually happening up the street this week. Some of them were at AAS. I don't know why I did this. It was just like somebody said something and it would get in my head, and then I would have to see it through to the end of, like, writing a parody song for it and filming the little video. They're very, very fun. So if you want to search for Astronomers Say Productions on YouTube, there's a bunch of them on there. I dabbled in TV appearances. Most of these are a little bit goofy. My gosh, like Lou Dot, so the very first one is up here on Fox Business News when the meteor exploded over Russia. Yeah, and Neil Tyson couldn't be everywhere all at once. And so I called that a bench clearer. Anybody that was even remotely interested in talking to the media, he gave me somewhere to go. And I got Lou Dobbs Tonight on the Fox Business Network. I had never been in, like, a live TV before, and I should have listened. Like, so I sat down in the makeup chair, and I was just like, do whatever you need to do. And then another woman came in who was going to be also a guest on the show, and, like, told the woman to do, like, natural makeup. And I was like, I'm going to be in trouble. I had fake eyelashes on there. I'd never worn fake eyelashes in my life. And of course, the first thing I did was, like, knock one of them off, and they were like, oh no. But still, Lou Dobbs was wearing more makeup than I was. And I was thrilled, you know, this was 2013, and so it was even before Fox News had like, and this is Fox Business News, which is different from Fox News. It didn't have quite the bad reputation that it does now. And I was actually pretty impressed with Lou Dobbs for having like a young woman on the show to talk about science. And the CUNY TV shows and, you know, local news. This is actually for Astronomy on Tap, which I'll tell you about. It was fun. But it wasn't without like challenges. And so one of the other things that I like kind of consciously put a lot of effort into, but like also thought I needed to hide for a little while, was like needing support from other people and not being able to do everything on my own. And so definitely classmates and collaborators were an important network of support. Being active on social media, like a long time ago, it wasn't a thing. It wasn't a thing that you like necessarily should be proud of. I think, and luckily there's a lot of leading astronomers who have made it a good thing. And I have made a lot of networks and a lot of connections and a lot of friends through social media. So not Twitter anymore, but everybody's on Blue Sky now. If you're on Twitter and you want Blue Sky invitation, it's in beta, so it's invitation only, but a lot of the astronomers have gone over there. So if you want an invitation, let me know, because I have invitations. And it's nicer than Twitter now. I've also, I am very proud of the relationship that I've developed with my therapists. It took me a while, and in fact, my first therapist built herself as an executive coach. But really, we shouldn't need to do this alone, and we shouldn't feel weaker or lesser than for needing help like this, especially therapy, especially in New York City. And one of the things that I've actually turned around and been able to publish is a peer mentoring group that started through APS. There was this E-Alliance thing that they got NSF funding for to put to connect women in physics together, and especially women. I think it was all people with faculty positions, but what it did was help you find an affinity group, so you could kind of pick what aspects of your identity you wanted to find people to be like, and they would connect you with that. And so I actually intentionally didn't search out astronomers here because I had already knew a bunch of astronomers. What I sought out were women physics faculty who were in kind of isolated departments. And so this is when I was at the College of Staten Island. I was the only woman in my department. And also it ended up eventually that we all had 2 kids, which was wonderful. And in fact, like 40% of them are named Max. And another 40% are named Clara. I'm not sure exactly why Clara, but Max for a scientist kid, I think is, you know, pretty obviously that everybody loves E&M. But it's amazing because all 5 of us, and I think, like, I don't know the exact statistics of this, but all 5 of us now in different areas of physics, kind of different subfields of physics, have gotten tenure, and some of them said they've moved institutions in a positive way. And so it's that we published what we do in terms of this distributed peer mentoring work, and we did it all asynchronously, and so we even started it asynchronously before the pandemic, but we kept it going, and all of us have recognized it as a very important way for us to like share our struggles and see that other people are going through similar but different things. And it's nice to know that your challenges kind of aren't just unique to you, and that you can also get through those challenges because you have smart people to help you find ways to figure it out. And so in my last like 2 minutes, I want to talk about the 2 big things that have kind of taken over my science work. I want to really explicitly call these science work, but wow, I think every single one of my social media icons is outdated here. So I call myself HQ. I coordinate all of the Astronomy on Tap events worldwide. If you haven't heard of Astronomy on Tap, now you know it, and it does what it says on the tin. Basically, it's astronomy outreach presentations in bars. This is where we used to meet at the Way Station in Brooklyn. Unfortunately, that closed down at the pandemic. But the one up there where I have the orange hair is on the Intrepid Air, Sea, and Space Museum under the butt of the space shuttle, which I still can't believe that happened. So let me tell you a little bit about what Astronomy on Tap is. This is also very pregnant. You know, remember I talked about like distancing myself from it. I didn't host the events as Emily Rice. This is DJ Carly Sagan. Now we have the same outfits, but I don't wear the wig as much. So Astronomy on Tap is multiple short outreach presentations in bars, and so we do other fun stuff as well. So trivia, music, games, prizes. We do it to make it really, really fun, really interactive, really engaging, really accessible. Like as headquarters, I try not to puppet master too much. Some people think I do, but I mostly try to say, hey, we did this and it works. You know, try it out yourself and do what works, you know, with the toys that you have in your sandbox. And doing that seems to have worked. So I can't take full credit for the idea because it was actually Meg Schwam that started it when she was a postdoc in New Haven. She did a couple events called Astronomy on Court. And there was some event that she came to in New York City and she said, you know, I've done these outreach events and I would love to do them in New York. And I said, awesome, I'm in, because my tenure track is taking away from my social life, but let's call it Astronomy on Tap to do it at a bar. And so I kind of wanted to, you know, Meg was very into wine and she knew all her computers after different types of wine, but I was like, I want to level this playing field a little bit. And so I want to take the wine snobby aspect out of it. And so we did it in April 2013. When I did things on Facebook, we actually had 6 different presenters, some of whom are still in the, so Gabe Perez-Giz is at NYU again, Adrian Price-Whelan is at the CCA, Meg is now faculty at Queen's University of Belfast, Ashley Pagnotta is faculty at College of Charleston. 6 different presentations in one night. Was too many, but now we've kind of gotten it down to a good kind of set of best practices, which is maybe 2 or 3 presentations. But even after this first one, it went so well that very quickly somebody else started one in Columbus, Ohio. It went back to New Haven. We went uptown a little bit. This was like at 103. And then we had astronomy on deck, we called it, on the Intrepid under the butt of the space shuttle by the end of 2013. And so through our education context at AMNH, they heard about it at the Intrepid. They had a bunch of champagne left over from some other event, and we got to do, I still can't believe we did that. And then we did a couple more after that. So whatever it was about this idea, like, really took off. And so much so that we have reached almost 2,000 events worldwide in the last decade. And I really do mean worldwide, like over nearly 100 locations. My map is probably out of date, but like a couple different places in Chile, in Bogota, in Hawaii, all across the US, a bunch of places in Canada, Tel Aviv, Korea, Taipei, a bunch of places in Europe. Paris is finally starting. Like, if somebody gave me $1 to $10 million right now, I would plan a world tour and go to all of these events because I just can't believe that they happen all over the place. They're so great. We did this was at the beginning of the pandemic, we did a 7-hour live stream to celebrate our 7th anniversary, and we actually started at Tel Aviv and went across the globe following the time zones. I still don't know how I did that with 2 kids at home. But what I'm really proud of is this array of all of the different logos that the different satellites have picked. And I try to do a AAS poster every year to talk about what we're doing. All of the satellites have really made it their own. Some of them have turned it into like a colloquium at a bar, which is not the best, but not the worst. But it's really a wonderful way to do outreach, but not necessarily just for the public. I think this is actually secretly, maybe not so secretly, outreach for us. So this is a lot of words, but I want to highlight the ones that we practice our communication. Like, it's much different to give a presentation at a bar where you have to fight for people's attention than it is to, you guys are all, you have to be here, you have to be polite, right? The worst thing you could do is fall asleep and snore, right? At a bar, you can get heckled, people are gonna get up and leave, you learn a lot more about storytelling, communication, and audience engagement and things like that at a bar, but it's also much lower stakes. You're not the top bill, you're not the only person speaking. You can bomb for 10 minutes and the rest of the night is still gonna be fun. It's gonna be fun. But it's also for us to network with one another. So especially in a place like New York City, it's Astronomy on Tap, New York City. It's not owned by any individual institution. And so we try to get a bunch of people from different places to present. And it's also a way to develop and practice skills beyond research. So things like project management, graphic design, promotion and marketing, social media, teamwork, leadership, budgeting, things that you might not be able to do in your research group or in your lab, but you can do on kind of a smaller scale and in a really interdisciplinary way with these events. And it's also fun. Like, I think that might be my new, I'm trying to figure out why I do these things and what they have in common, and I think that's just this is my idea of fun. Oh, and so this is very new. I made a QR code because we've kind of only started to ramp up events in New York City again. We finally have a second location in Manhattan that's going to happen later on this month. And so I've made a survey for people to show interest if you want to present at an Astronomy on Tap. I recommend attending first to see what they're like. And for that, go to the astronomyontap.org website. And so I'll circulate this. There's also an outreach list in New York City. It's a Google group, and so it's Astro-outreach-NYC, I think. And I'll send this around to that very, very soon. Last but not least, in the -5 minutes that I have left, I dress like this on purpose now. So this dress is from STARtorialist. It's solar DKIST, so the Inui Solar Telescope on Maui. It's one of the first light images of a sunspot from that. But STARtorialist is this thing that has turned into, I don't know, it's an online shop now, but it's more than that. It's like the accumulated enthusiasm of the astronomy community. It started out as a blog, but it's become so much more than that. And I think the reason why it is so popular and so important to me is that fashion, which can be seen as, superficial or kind of, I don't know, esoteric or something like that, is actually a very human, very personal thing. And it's something that we can learn from in order to make science more like the positive aspects of fashion. So creativity, inclusivity, expressiveness, functional but aspirational at the same time, all of these things that, go into dressing, you're dressing for something, whether or not you, kind of recognize it. And we can use these in ways that really make science better, in my opinion. So it started as a blog for public outreach. Me and Summer Ash did it when Summer was the director for outreach at Columbia. We just kind of noticed ourselves wearing astronomy-themed stuff for outreach events. And we're like, hey, there's so much of this stuff that we can buy, but we can't afford it. We can't fit it all in our New York City closets. So why don't we make a blog? And so we met at the Hungarian pastry shop up by Columbia. We started this blog. And then after a year and a half of having the blog, we presented it at the AAS. And so here's us with our first poster. And I really, I had a nightmare before it. I thought there's no way that I'm going to be taken seriously. I didn't have tenure yet, but I was on the tenure track. And I was like, maybe it's the end of my career, because I pictured people coming over and being like, what are you doing? This is a science conference, not whatever this is, get out of here. And instead, and I'll be honest, it was the little old white guys that were saying that to me in my nightmares. The little old white guys came over and they said, I love this is so great, where do I buy presents for my wife? But everybody we weren't the only ones that were dressing, with the astronomy themed stuff, but somehow it became, we kind of, we caught the spark or something like that. And so I joke that we became the dark energy, because we, in addition to finding and curating this stuff, we kind of found our own connections on the way and ended up causing the expansion of this astro fashion to accelerate. And so I really thought when we started the blog that it would just be this fad, it was kind of popular for a little while and then it would go away, the same thing that, fads come in and out of style. But it didn't happen. We were the busy poster 2 years in a row, the busiest I've ever been at any poster that I've ever presented. And then Debbie Kowalski, who was up there with Jupiter behind her, was the exhibits manager for AAS, and she said, we used to have people sell stuff at conferences. Why don't you guys coordinate that now? Because the conferences got big enough that the booths got too expensive for the individual kind of designers and companies and things like that. And so the first AAS where we had a booth, we kind of had a showcase booth of coordinating these different independent designers and people with Etsy shops and things like that. That was also the busiest I've ever been at a AAS conference. And then Kelly Cruz, who's my BDNYC collaborator, was like, so the showcase booth, we didn't actually sell anything, we just had business cards and flyers and things like that. And then Kelly was like, we can do resale and wholesale, we're astrophysicists, we can figure out this small business stuff. And so she did basically, and we sold stuff at the next conference after that. And that was also the busiest I've ever been at a research conference. And so now we design stuff. You know, we had a jeweler who was making things that somebody said, oh, this looks like a Sloan plug plate. And we're like, now it does. And we made it into an actual Sloan plug plate, you know, based on the engineering specs and stuff like that. We had this designer create 3D printed JDRS telomeres even before it launched. This is the Dare Mighty Things Mars Perseverance skirt. So she designed this, it went viral on TikTok, and I said, let's get this in the shop. And luckily it still went viral in the shop, and that kept us alive. And so we still go, we have the shop online now, and we go to conferences, and so the AAS conferences, and we have students help us staff the booth at the conferences. We collaborate with astronomers, like every single thing, I know this looks like a random hodgepodge in the picture, but every single thing has a story here. Either an artist who said, oh my gosh, I've always loved space, but you know, I couldn't do the math, or you know, I didn't really like the physics or something like that, to astronomers or other scientists who have this designy side and have their own Etsy shops. It's very, very wonderful that we get to kind of like combine those two communities. And so this is like the one of the best ways that I can find for why I do this stuff. It's this concept that's called Ikigai. It's supposed to be Japanese, but this is from the Toronto Star, so I don't know how like culturally accurate it is. There was a New York Times article recently that called it mattering, which is also a nice kind of science pun. And so this is like, you know, my Ikigai isn't in pure research. It's not in the thing that would, you know, you stereotypically think of when you think of science. But it's why I'm here. It's this combination of things that I like to do. It does make me unique, I think, as much as I try to like make sure that it affects everybody else as well. And then it also like it keeps me here. It's the thing that I like to do day to day. And I intentionally, when I do talks like this, I try to call this science, because one of the things that I strongly believe is that all of these things that we do, it's, you know, it's not just the things that fall under this narrower, smaller umbrella of research, but all of these other things are still science. So the policy, the teaching, the mentoring, the curriculum design, all of these things are science. I never would have thought that I would also try to convince you that like fashion design and business would be under this umbrella. But it most certainly is, and STARtorialist is probably the single thing that I do that is more similar to research than I ever would have expected. An online shop is basically just a database. And so especially for the students and for the mentors to be aware of, here are lots of other ways that you can be involved in science that are not just the research. They're related to the research, but not purely. So some outreach projects like Skype a Scientist, letters to a pre-scientist to help you work with classes, AstroPie, you know, we've been much better as a community about giving the credit to software development, things like that. Story Collider is similar to Astronomy on Tap, but it's no slides, it's telling stories about science. And of course, Astronomy on Tap, I think is wonderful, but Astrobites for writing. And I do actually have the rainbow umbrella, which is really nice. And so here's my email address. If you, I have a couple minutes after this, but thank you for staying. I'm still running over. And I'm gonna have to run to pick up one of my kids at 3:45 or so. But my email is emily.rice@mhc.cuny.edu. And especially the students, I'd love to talk more with you and have you come to Astronomy on Tap, especially. Thank you.
Right.
I'm talking really fast.
I think we have time for a couple of questions. Can I ask just a slightly random off-topic science question that's been stuck in my head since several slides ago?
Yeah, oh yeah.
There was your the NSF proposal brown dwarf stars atmosphere.
The atmosphere one,
slides.
yeah.
Is there corundum in stars?
Yes.
In the upper atmospheres of stars? Like corundum is like rubies and sapphires.
Yep. Christiana Helling, I went too far. There is in fact corundum. Oh, and now I'm getting the rainbow. Christiana Helling is a theorist who does a lot of the kind of microphysics modeling of the solids that are formed, and yeah, like corundum. There we go. Oh, don't quiz me on it. Perovskite and corundum. So, and perovskite is that opals?
I think so.
Yeah, corundum is magnesium or aluminum silicate, and it's depending on whether the inclusions are I'm forgetting the details of the mineralogy, but like, yeah, corundum is basically sapphires and emeralds. No, rubies and
Yeah.
I know.
Did somebody write a big press release saying we found rubies and sapphires
Yeah.
and stars?
Yeah. And so it's brown dwarfs. It's the brown dwarfs that are, but like they, some theorists really run with it and say, these jewel planets or something like that. Yeah, it's not quite that. There was also the diamond planet where it was the really high density, really carbon rich planet, but I think actually that detection was a little bit weird. But these ones, I can't promise how they're going to be cut or anything like that. Yeah, they're going to be pretty raw. But I think this is great to think of, especially if you go to the Museum of Natural History and go to the new Hall of Gems and Minerals and see all that stuff there. Like, and they've got a big piece of beryllium with a picture of JWST and stuff like that. Like, yeah.
I think when Jackie came here, she also talked about hematite clouds in other brown dwarf models, which that's rust. So
oh yeah,
rust-based clouds.
Yeah, there's a lot of wacky stuff going on here. Yeah.
Can you see like stellar variability change in like the younger dwarfs?
Oh my gosh, yeah. I can do, like, that's one of the things that BDNYC is doing now is the variability of these objects, and woo, like, yes. I kind of talked about these like they're very, very static things. Absolutely not. They're rotating. We're trying to get at the rotation periods, but as they're rotating, all of these clouds are changing. And so especially when there's disequilibrium chemistry, especially when there's clouds in the upper layers. So we think that for the younger objects with these more extended atmospheres, the dust that forms can kind of stay in the atmosphere longer, stay high in the atmosphere longer, but it's also, there's no reason to think that it's going to be like uniform coverage. It'll be patchy, it'll change with time. Yeah, think about all of the the wackiness in all of the outer planets in the solar system, and then multiply that by a factor of 10. Like, that's what the brown dwarfs, we've got aurora on brown dwarfs, we've got magnetic fields. So the Jupiter magnetic field, a lot of it is from the aurora on Jupiter is from the interactions between Jupiter and Io, for example, but the brown dwarfs we think also have their own magnetic fields and also have auroral activity, and so we can detect some of them in the radio.
Can you see polarization of light too?
What is it?
Can you see polarization of light from the?
Yes, I believe so. I don't know how much we've done with polarization, just because they're so faint.
Gotcha.
And so the polarization is really, really tricky to do, but we did try to do it for a while. Yeah.
Can you give a plot of like luminosity versus age for these like planets and brown dwarfs? Yeah, that one. So you have like the 1 and Jupiter mass like going forth. I mean, is that actually like for Jupiter, our Jupiter? I mean, can I assume that Jupiter was that bright or that hot temperature just early in the formation of the solar system? Like how
probably not, because these are really evolutionary models, and what they the kind of the more planetary formation models are going to have different, they're called either hot start or cold start or warm start. I forget what the actual differences in between those, but it's like depending on how big the core is, what the temperature is at formation, things like that. And so I wouldn't necessarily directly apply this to Jupiter, no. This is kind of taking the kind of more free-floating things, free-floating formation, independent formation, and kind of scaling it down.
Right. I mean, is there any idea how hot Jupiter was to start off, and like, was it at one point hot enough that its moons were at room temperature, or?
Oh.
And if so, like, how long that would be? I mean, I'm just kind of curious.
Yeah. I don't know off the top of my head. Yeah. And I don't know. Yeah, and it's also they've all been moving through the solar system, and so that like other people do know a little bit more than I do, but even I think what we know and how much things have moved, I think is still pretty open.
All right. Well, thank you all for coming. And
Yeah,
as somebody who has both bought stuff from STARtorialist and talked at Astronomy on tap, I also wholeheartedly recommend both.
Yeah, very fun.
Let's thank Emily again. Yeah, stop the sharing. I could just end the meeting on the big one.